probability distributions. So basically, the physical information, again, is not visible in the equation, but still is present in the data. Of course, one may say that you make an implicit use of physical information, and one may say that you don't use all the physical information that is available. We don't use all of it. Because, for instance, I have information on the catchment, which I'm not using. Not only the area of the catchment, I'm not using information on the land use, I'm not using information on the geology, but I have this information. And therefore, one may for sure say that we are not using all of it. So one may say that there are methods which have more physical information embedded, but still, the physical information here, and there is a remark in my notes, is used. Okay, now let's turn to another approach, not a probabilistic one, or let's say another approach that it still uses probability, but in a very different way, and it complements probability, integrates the probability analysis with other considerations. And why I'm talking about this different approach? Because so far, the methods that we used are based on data analysis, so you need data. And what if data are not available? What if the location, which is represented by a river cross-section, is ungauged? It's not gauged, it's ungauged. And therefore, I am introducing a relevant problem in hydrology, and not only hydrology, engineering, which is marked with the term prediction in ungauged basins. I could also say estimation in ungauged basins. So let's take the term prediction in a wide sense. Prediction in ungauged basins. And if you try to Google prediction in ungauged basins, you would find thousands of entries. Why is that? Because this is a classical problem in hydrology, and it's the situation which is most frequently encountered. Because it's very rare that you have data for the location of interest. It's very rare because, you know, the number of gauged river cross-section is very limited all over the world. So it's unlikely that you have data collected where, precisely where you have to design a bridge, a levee, an embankment, or whatever. In most of the cases, you are required to refer to an ungauged location. And therefore, there is a very extended literature in hydrology on this problem. Also, from 2003 to 2013, the International Association of Hydrological Sciences, which is the most important international worldwide association, scientific association dealing with hydrology, in this period they launched a scientific decade. A scientific decade is an international initiative where an important body says we need 10 years of research on this emerging issue. And the scientific decade was called Prediction in Ungauged Basins. And therefore, they got a lot of papers published and a lot of web pages reporting on the progresses that have been done, and also a summary book was published titled Prediction in Ungauged Basins. And as I said, this is a frequent situation, and then the question is, how can I estimate the peak river flow if I don't have data? And it may seem like an impossible problem, but actually, in the professional world, people devised very practical methods for solving this problem. Still, there is uncertainty, and you may understand that the uncertainty is for sure higher with respect to the gauged situation. Still, in the gauged situation, I said there is uncertainty, but of course, in the ungauged situation, uncertainty is more significant. So let me now start mentioning the methods. And the first concept that we need to introduce is hydrologic similarity. So basically one idea is let's use hydrologic similarity to estimate the peak river flow in ungauged locations. And what is hydrological similarity? It means that there is similarity in terms of hydrology between two cross river sections. One is gauged and the other one is ungauged. The ungauged one is typically the location where you have to design. You don't have data there, and then you look for a similar, in terms of hydrology, a similar location where you have data. And the idea is to extrapolate the information, the estimate, from the gauged to the ungauged location. You may wonder how this is possible, and let's make clear that it's possible that two different rivers behave in the same way. If they have similar climate, similar geology, similar extension of the watersheds, similar morphology of the watershed, they may behave in the same manner. So you can indeed extrapolate the information from one river to another, but of course you have to make sure that they are similar. So this is the concept of hydrologic similarity. And an interesting, or let's say, a very simple example is the case of one river where you have a gauged location, let me put a G here, and you are required to make your design in an ungauged location which is placed on the same river just upstream or just downstream. In this case, it's clear that there is similarity. Same river, same watershed. There is, of course, a bit of difference in the geometry of probably of the cross-river section, but if they are close, the geometry may be similar. There is some difference in the catchment area, because of course if this one is upstream, even if it's just a bit upstream, of course it refers to a catchment of reduced extension. Think of what happens if a tributary goes into the river here. The tributary brings a contributing catchment, and therefore in this case the catchment extension is of course different from the U section to the G section. But if they are close, if there are no tributaries, this is a very meaningful example. And this is done very frequently by professionals. If they have to refer with an ungauged location, what they do is to look downstream or upstream to see if there are data, to see if there are gauged locations. And if they see that there is a gauged location just upstream or just downstream, they are happy, and they estimate the peak river flow for the gauged location, and they take the same peak river flow for the ungauged location. Of course, if the distance is reduced. This is done very frequently, and therefore this allows you to solve a lot of problems, because in the same river, you almost for sure will find, if the river is important, a gauged location. So in many cases you will resolve your problem in this way. And also, if the location is downstream, if the gauged location is downstream, you can take the estimate as it is, because you are on the safe side. If you move upstream, the peak river flow should, in principle, decrease, because it decreases the contributing catchment, and therefore it may decrease. There are exceptions to what I'm saying, but in general, especially in mountain basins, if you move upstream, the peak river flow decreases. And so basically you are on the safe side. And for this reason, when one looks for a gauged section, typically the engineer first looks downstream. And then if he doesn't find any location downstream, then she may look upstream. And of course, if we look downstream and we see a gauged location at a distance of 10 kilometers, and we look upstream, we see a gauged location at 1 kilometer, of course we will take the upstream one because it's much closer. even if we are not, strictly speaking, on the safe side. As I said, this allows you to solve many problems. To make an example of a river where the upstream peak river flow is not greater, but of the same amount of the downstream one, I may mention the Po River. If you look at the peak river flow at Piacenza, which is located about 200 kilometers from the closure, the peak river flow at Piacenza is the same as at the closure. It doesn't decrease because the river is strained, and therefore it's, there are levees and the river cannot expand. So basically when the river is strained, it may happen that moving downstream you get an increase or a not decrease of the peak flow. But when the river is untrained, and for this reason I said mountain basins, usually moving downstream you get an increase of the peak river flow. Now, so far I mentioned the case in which you get the estimate in a gauge location and you directly use it in the ungauged one without making any change. You use the same estimate. But what if there is a significant distance between the two locations? In this case, if you refer to a gauge location that is much downstream, or it may be located in a neighboring river. Because think of the situation of a river where the ungauged location is here, and the gauged one is much downstream, and you have a neighboring river, or a tributary maybe, for which you have a gauged location here. So you may prefer to refer to the neighboring river even if it's not the same river, because the distance between the two locations is lower. This is, to some extent, a subjective decision. I will tell you some more details in help you to identify the most similar location. But for now, let me say that you may prefer a location in another river. In any case, in both of these situations, it's clear that you cannot take the estimate as is. You need to make a transformation. You need to make some rescaling. Because there is too much difference. The sections are not very close. So you need to make, again, some rescaling. So the question is, how can I make this rescaling? Here there is one example, and you don't need to look there. I'm just rewriting here. So the question is how to rescale the estimate that I obtained in the gauge location. And the estimate can be obtained by using, for instance, the annual maxima method. So for this reason, probability may be still used here. So how can I rescale the estimate that I got in the gauged location to the ungauged one? One possibility is if I indicate the estimate in the ungauged location with the symbol QT, and the T is the return period. One possibility, and let me make a schematic. Here there is the section, here there is the section where I want to estimate QT, and this section has an area A, catchment area A. Here there is the gauged location. I call it Q star. I call the peak river flow estimated here Q star T. Star refers to the gauged location. And let me just put a U here. And here I put A, and here A star. So A and A star indicate the catchment areas in the gauged and ungauged locations. Star stays for gauged location, area of the gauged location, catchment area. A without star stands for the area in the ungauged location. So we may write that Qt divided by Q star T is equal to A divided by A star to a power of alpha. Should be the same that is written here. Let me see. Yeah. And therefore, you can estimate Qt in this way. Qt, namely the peak flow, the design flow in the ungauged location for retro period T is given by the design flow in the ungauged location for the same retro period times the ratio between the areas to the power of alpha. So basically, you see that there is a rescaling, and the rescaling is operated based only on the catchment areas. So it is assumed that there is a dependence of the peak flow on the catchment area, and this is the only dependence. So the rescaling is done based on the catchment area.
So if the absorption in two areas is different, what then?
Yeah, it may be different, for sure it is different, but in this case it's not considered. It's assumed that the runoff coefficient is, it's not really the same because there is this exponent alpha. If the exponent alpha was 1, then it means that what is called the specific contribution to the peak flow is the same in the two sections. What is the specific contribution? It's the peak flow per unit catchment area. So if you cancel this alpha, if you assume that is 1, what do you get from this relationship? So let me make this example. Let's assume that alpha is 1. Let's assume that alpha is 1. And then if alpha is 1, what I get from this relationship is that Qt divided by A is equal to Q star T divided by A star. So you see that the peak flow per unit catchment area is the same, but only if alpha is 1. If alpha is not 1, and actually the literature says that it's not 1, it means that the specific contribution is different, and it means that for the same rainfall, you have a different river flow, which means that the runoff coefficient is different. And indeed, the literature says that a reasonable value of alpha for Italy could be 1/3.
For how much distance we can apply this rescaling?
Let me move forward. First of all, let me make a comment. What does it mean is alpha is equal to 1/3? You can easily test, you can easily see that if alpha is 1/3, it means that alpha is not equal to 1, and therefore it means that the specific river flow is not the same in the two sections, and precisely the specific river flow is increasing for decreasing catchment area. So you can easily test it. If you decrease the catchment area, the specific river flow increases, which is what happens in reality. In reality, you expect a higher specific contribution to the peak flow and a higher one in small catchments. And why is that? Because small catchments, in small catchments, it's more likely that if it rains over the whole catchment. In a large catchment like the Po River, if it rains over the Alps, probably it doesn't rain over the Apennines. And so you get a kind of smoothing of the extreme event. In a very small catchment, an extreme rainfall may cover the whole catchment, and therefore it's not smooth. Also, there is another reason. Small catchments typically are mountainous catchments, which are very steep. And being very steep, you understand that there is no smoothing action by the catchment. All the water, when it rains, it goes directly into the river suddenly. And this is why, in terms of a specific flow, the small catchments, mountain catchments, are more dangerous than large catchments. So let's think, for instance, to make an example, the Po River. The Po River has an extension of the watershed which is 70,000 square kilometers, and the peak river flow for 100-year retro period is about 12,000 cubic meters per second. So if you divide the peak flow by the catchment area, you get about 0.1, some more, let's say 0.15 cubic meters per square kilometers. So this is the specific flow. It is expressed in cubic meters per second per square kilometer. So for the Po River is about 0.15. You divide 13,000 by 70,000, and you get about 0.15. The Secchia River, if you look at the peak river flow that we estimated for 100-year retro period, is about 914 cubic meters per second. Then the catchment extension is 1,200 square kilometers. So if you divide 900 by 1,200, you get almost 1 cubic meters per second per square kilometer. So you have 10 times, not 10, 6 times the Po River. So this is a clear explanation. And if you get small watersheds, you may get in Italy. It was experienced during the flood that occurred in Tuscany in 1996 when many people died. They experienced up to 50 cubic meters per second per square kilometer, which is really amazing, 50. It means that a catchment, a very small catchment of like 2 square kilometers delivered like 100 cubic meters per second. So this is the order of magnitude. In Italy, you go from 0.15 of the Po River to up to 50 in the mountainous areas, in the mountain areas where also there are steep catchments and heavy and extreme rainfall events. So, the second question, the question that was asked here is up to what distance? This is a bit tricky because what is important is that the catchment is similar. So two catchments may be very dissimilar even if they are very close. Think of the case of the tributary. So basically, if you have a river and then you get a tributary entering here, and the tributary is very important, you may have two cross-sections which are very close, like 100-meter distance, but the hydrology is completely different because the tributary is bringing different situation into play. So, in this case, even a very close distance may make the two sections very dissimilar. In other cases, we experienced a very strong similarity between catchments located one in Europe and the other in the United States. And they were proved to be very similar. In which way? Shape of the watershed, extension of the watershed, geology, land use, land cover. You may indeed find catchment in New Zealand that look very similar to catchment in Europe. So basically, it's a kind of personal and to some extent subjective evaluation that you have to carry out. You should look at the main hydrological features of the catchment, and they include the meteorology, they include the morphology, they include the geology, the land use, land cover, the human impact, and you should make sure that the catchments are similar. Keep in mind that, and I'm slowly moving towards the next method, keep in mind that people devised more complicated relationships. So for instance, recognizing that the extreme rainfall is different, people introduced, and sometimes they use, also the ratio between the rainfall extremes. In this relationship, they introduce not only the ratio between the areas, but also the ratio of the rainfall extremes. So they first estimate the extreme rainfall, like daily rainfall for a relative period of 1 year, of 100 years, in the two catchments, and then they get a ratio, and they use this ratio, they introduce this ratio between rainfall in this relationship. Because of course, if you see that there are differences, or you may look at the extension of the urban area and compute the ratio between the extension of the urban areas, and then use this ratio there. So there are several extensions of this method in order to account for dissimilarities, to make, to explicitly account for dissimilarity. And now I introduce another question. What if you have two ghost locations? Of course, there is an option which is to use only one of them, but this is not really a good option because it's not efficient. It's not using all the information. Another option could be to estimate the peak river flow by using the two alternatives and compare to get the uncertainty. This is more reasonable. Another option is to make a kind of mix. Like I'm using both locations in a mixed way. And this is probably the most interesting option, because think of the situation in which you may have 10 locations. So the ideal thing is indeed to make a mix. And how to make this mix? So I'm slowly introducing the next topic, which is, I think I should have probably called it before calling into play the index flight method, I should have put an overarching title, which is a regional analysis. When you have several ghost locations to refer to, then we may apply the regional flood frequency estimation or regional analysis. Why regional? Because you refer to several locations, to several ghost locations, and therefore you refer indeed to a region. And this is an interesting option because if you could identify a method that is valid over a region, this method could be applied to all the ghost locations of that region, so not just one. Like in this case, if you have another ghost location downstream or upstream, and the method works for one given ghost location, it may work well also for the other ones. So it's indeed the regional analysis is an interesting option. And the best way to explain, to introduce the regional analysis, because it's in principle very simple, but of course one needs to introduce it in an efficient way from the point of view of education. I think the best way to introduce the regional analysis is indeed to introduce what is the most used regional method, which is the index flood. So what is the rationale behind the index flood? First of all, it is assumed that the method is valid over a region, geographical region, which is called homogeneous region. Be flexible. The region doesn't need to be unified. The region could be formed by several catchments, one in Europe, one in New Zealand, one in the United States. So we don't need to refer to a unified portion of the geographical area of the globe. It could be formed, the region, by spots, which are located everywhere. And this is a recent development. In the past, regional methods were applied only to unified regions. And then we recently realized that indeed there are similar catchments all over the world, and then it's inefficient to limit the attention to a unified region. Let's refer to what we call a homogeneous region. And homogeneous, what does it mean, homogeneous? It means similar. It means a region where we can apply hydrologic similarity, where we can consider that the hydrological features are similar. Of course, there is a first research and practical question, which is to estimate this homogeneous region. And I'm not getting into the details because it's a bit complicated. Basically, what it's done, it's just enough that you know in principle what it's done. Basically, in principle, people look at the gauged locations and analyze the data, and they find some statistical similarity in the data. And also, they look at the catchment behaviors in that region, and they find some similar information. So there is a mixed approach, a mix between statistics and hydrological analysis, and people conclude that two catchments are similar. Data analysis is important in this case, so they look at gauged locations to get a confirmation that there is not only what we think is hydrological similarity. There is indeed statistical similarity in some way, quantified in some way, which we do not inspect. Okay? So basically, from your point of view, you are an engineer, you may be required to apply a regional method, and the homogeneous region is given to you, because this is a task of researchers. To identify the homogeneous region is a task of researchers, and therefore, basically, as a professional, you are given the way to identify the homogeneous region. Then the index flood method assumes that for a given location in the homogeneous region, the peak river flow Q, which refers to the location I in this case, it's a geographical coordinate for me, which identify a location. And the return period T is expressed as a product. I look at the symbols because I want to be consistent. And the product is between two quantities. The first one is, let me see, I get the symbol. X. Sorry, the location is X. Sorry for that. I wanted to make it, to use the same symbols, and I made a mistake. The location is X. So there is the product of a first factor, which depends on the location, which is multiplied by a second factor, which depends on the return period. So the idea is split the dependence on location and return period in two factors which are multiplied. The first factor is called the index flood, and we will see what is that. And the second factor is called the frequency curve. And sometimes it's also called the growth factor. So why frequency curve? Because this depends only on the return period. So it depends only on the frequency of the flood. And this frequency curve, you see, does not depend on the location. So it means that it's valid over the whole extension of the homogeneous region. The index flood, conversely, doesn't depend on the frequency, on the return period. It only depends on the location. What is the index flood? The index flood is the average value of the annual maxima. Is the average value of the annual maxima. So what is the index flood? For a given location, for a given cross river section, is the average value of the annual maxima. Average. So you see, when I say average, it means that it doesn't depend on the frequency. There is no frequency there. It's just a statistic. It's one value, depends only on the location. The frequency curve, on the other hand, it describes how this average is increased for increasing return period. I think I already mentioned to you that under certain assumption, the average has a return period of 2 years. The average has a return period of 2 years. You can imagine it, because when you are on the average, it means that in 1 year you get